In the last video, we were looking at the new C#9 feature of records, and one of the things we discussed in that was the various ways that we can compare objects for equality. And so I thought I'd talk about that this week in slightly more general terms, looking at classes and structs as well, and particularly focusing on something that I didn't really mention last time, which is the getHashcode method, which is available on all objects and is a really very useful thing to employ to get your code to work efficiently. So if we take a look at the code that I've got here, what I've got is very similar to what we had last time. I have put together three different point types, a class, a struct, and one of the new records. So I've called those point C, point S, and point R. And just to keep things simple, they're just two-dimensional integers X and Y for each of those. And then if we just look in the main program, we can see I've just created a couple of instances of each of those, and they have exactly the same values, all of them. X is 100, Y is 200. And if we look at the record, actually, that's probably the simplest one to go with, because that's the one where pretty much everything is created for you. So we can do things like, say, maybe just have a console write line of if R1 double equals R2, so we can do a comparison there. And that is, for a record, going to give us what's known as a value comparison. So it's not telling us that these are the same point, they're simply saying these are two different points but with the same values, 100 and 200. Similarly, we get generated for us with a record a not equals that just does the reverse of that, but we also get things like a equals, so we've got a method there called equals, and in fact we have two overloads of that. We've got the equals that takes an object as a parameter, which is inherited from the object base class, and then we've also got the overload that takes specifically a point R, and that is actually an implementation of the interface I equatable. So two different equals is in there. And then we also get with a record, again inherited from the object base class, but overridden, we've got this getHashcode, which we're going to talk about more later on. And so the nice thing about records is all of that is given you as soon as you declare a record, and although you can modify the behaviour of each of those things, it's not something you that commonly have to do, just leave it to the auto-generated code to do it. But when it comes to structs and classes, you don't get quite as much for free. So if we look at classes, for example, we can see that we get a double equals operator with the reference type, but all it's doing is comparing to see that those two are the same object, not different objects of the same value. So if I say C1 double equals C2, we can see that gives us false because they are not the same object. We also have the dot equals, and this is where things start to get a bit interesting. So it's got an equals because it's inherited from the object base class. And if we look at that one, we'll see that is also giving us false because the default behaviour of the equals is the same as the double equals. It is giving us a reference comparison saying, are these two the same object? So you can see when I compare C1 to itself, it's giving us the fact it's the same object. But equals should mean value comparison even when we're doing it on a class on a reference type. So one of the first jobs we really need to do if we've got classes is we've got to write our own equals so that in this case we will get true there because they're both 100 and 200. So let's do that. Let's go back to our point. And so the first thing I'm going to do here is not override the base class. I'm actually going to implement that I equatable interface. So let's do that. So let's do colon I equatable, and it's generic for the same type, so we do it for point C, and then if we implement that, then it just gives us the stub, so there we've got what we want. Now the obvious thing to do is we are going to say return, and then we can say x equals other dot x and y equals other dot y. And so now we should see, having done that back in the program, that's what's going to be called there. And so now we're getting true because they've got the same value. Whereas if I were to change that to say 300, we're getting false. And so that's again working correctly. However, there is a slight problem that we've got in there, which is that this other is not necessarily a point C. It's a point C or anything derived from a point C. And in almost every case, if two objects are of different types, even if those types are related by inheritance, then they are not equal. And so what we have to do here is, as another check, we're going to say this dot get type equals other dot get type and all the rest of it. So it's only going to work if they are the same type and the x's and the y's are the same. So that's just a safety check we put in there. Doesn't make any change to the behavior. We're still getting that working correctly. You'll notice it's putting a little warning here saying if we implement iEquatable, we should also override the equals from the object base class. And so let's just do that. Again, a bit of code generation. But all we need to do, as you can see, it's generated it for us, is just call the other equals. And in this case, we just do the as to convert the type. And so that will work correctly. That does actually show us another thing we really need to do. And that is we've got to check that other is not null. So as that stands at the moment, if I were to set C2 to null, and run that, then we get an exception because we haven't checked for null. So what we need to do in here, as another check, we've got to say if other does not equal null, and etc, etc. And so now that will work safely. So when it's null, we're getting false because the object doesn't equal null. And when we've got a value in there, then we'll get true or false calculated correctly. Now, because this is a class, what we don't want to do is implement double equals and not equals, because they, for classes, should remain just doing the reference comparison to see if these two things are the same object. So in a class, the behavior of the method equals and the symbol double equals are actually different. If we were doing this on the struct, then we could just, in our double equals and our not equals, refer them to the equals method. If we're doing it in a record, that's already done for us automatically. But you'll notice we're getting one other problem here. It's giving us a warning saying that now we've overridden object.equals, we should also override object.getHashcode. And this is where we need to start discussing the idea of hashcodes. Essentially, what a hashcode is, and it's something that's used in all sorts of different areas of software development, is if you take a class or some kind of data structure, you want to be able to put that through an algorithm that produces a number that represents the data. And you want to do it in such a way that if ever you have two objects with exactly the same data, they should always produce the same hashcode. And so that's what the idea of a hashcode is. Now, I say that's used in lots and lots of different situations. When we're using it within C#, within .NET, we have this getHashcode method, and it returns you an int as the number. Now, in other circumstances, you might have bigger numbers, but in this situation, we have this int 32 bits. So every object in the entire of .NET can be represented by a 32-bit number, and if two objects are in the same state, they will have that same number. Now, the simplest thing to do as an example for this is just to look at an integer itself. So if we just put in a couple of ints, so let's have an int x equals 1, 2, 3, and an int y equals 4, 5, 6. Then if we write out the hash codes for those, so x.getHashcode, remember it's available on the object-based class, but it's been implemented for the int class. The thing we see is the hash code for an int is the number itself. There's no need for any processing whatsoever because we've got this rule obeyed that every possible value of int will produce this particular hash code. So there, it's very simple. But when we're looking at more complicated objects, there has to be some sort of work being done. So if I, for example, have a string str1 equals hello, and then we just have str1 dot get hash code, then we'll see we get that particular number. And if we make any change to that, we can see that we get a completely different number. So different values produce different hash codes. But if we have two objects with the same value, then they are guaranteed to produce the same hash code. So we can see there, they're both giving us that same number for the hash code. Now that brings on to one of the interesting things about hash codes, which is although a particular string like hello will always give us the same hash code, that hash code itself is not going to be unique. Because a hash code is an int, 32 bits, there are only 2 to the 32, about 4 billion different possibilities of what that can be. And clearly there are vastly more possible strings than that. And so it's possible, unlikely, but possible to get two strings that are the same value. And just to demonstrate this, it's actually rather harder to find these in .NET Core than it is in .NET Framework. But I've got a .NET Framework program here, and what I've done is I've created a string S2, which is just AA, and then a string S1, which is actually 3 characters, which aren't really printable. I've got a 0, a 61250, and a 46207, none of which can actually be displayed in the font we've got on the console. I generated this just with a brute force approach by running a little program and seeing if I could get something to match AA. So we can see that we've got those two things as rather different. As I say, S1 won't really print, but if we run that up, we can see that they've both got the same hash code, even though we're printing out AA, and then we've just got this space, question mark, which are those 3 characters that it can't really print. But the point is, same hash code. Really doesn't matter that they're not unique because of the way they're used, which we'll see in a moment. If we go back to our other program, what we need to do is start writing our own hash code for our class point, because if we take a look at what we've got here, so if we just go here and we say console write c1.getHashcode, same for c2. Now, because c1 and c2, although they're different objects, have the same value, they should be giving us the same hash code. But they're not. You can see we've got different numbers there because the default implementation of getHashcode essentially gives us a number that is based on the reference. So although if we did C1 twice, we'd get the same number. If we do C1 and C2, we're getting different numbers. And that is wrong. That is why, back in our point, we're getting this warning saying if you've changed the meaning of equals, which remember originally did a reference comparison, you also need to change the getHashcode to work in the same way. So let's do that. Let's do an override of getHashcode. And what we've got to do is find a way to form up one of these numbers that is guaranteed to be the same if the values of x and y are the same. Obviously, again, we're going to hit this issue that there are going to be more possible points than there are hash codes because a point contains 2 integers and the hash code is made up of 1. But there's various ways we can do it. One way that you sometimes see is just to take the integer values and do an XOR on them. So the hat symbol is a bitwise exclusive, or it takes each bit, does an XOR, and so that will produce as another integer based on those 2 integers x and y. And so we can see now, back in the program, we're printing out the 2 hash codes. We get the same value, just 172, which is what we're getting for the XOR of those. But if I were to change that number, say, then we get a different XOR, and so we've got a different hash code, and so that's working in the way we want. It does have a slight problem, however, in that the XOR is what is known as commutative. That's to say, x hat y is going to be the same as y hat x. And what that means is that if we had our 2 points as 100, 200 and 200, 100, we would get them with the same hash code. Again, as I said, that doesn't hugely matter. It won't change the behavior of your program, but it could have efficiency reasons. We'll see why that is later on. But it's something you want to try and avoid. So one trick that you'll see done for this sort of thing is maybe if we can turn this into a non-commutative operation, maybe by doing something just like this. If I were to say, let's XOR x and y times 2, then now clearly it's going to be different depending on which way around x and y are. And so now we can see that we are getting different hash codes, not particularly good ones, you'll notice, because 0 might come up in all sorts of situations because of the way these relate. So there's actually a number of better ways, algorithms you can find online for combining 2 or more integers to produce further hash codes. But actually, there's a data type provided for us within the .NET library that does that and saves us even thinking about it. And it's called, unsurprisingly, hashcode. So what I can do is just get this hashcode data type, and then it has a method called combine, which basically takes the objects we want to combine. So in this case, it's just x and y. And then underneath the covers, it calls their hash codes and combines them in a much more sensible way. So what we'll see here is now, if we run that up, that we are getting different hash codes, even though the only difference between the objects is we've swapped over the 100 and the 200, and if we swap them back, we'll get the same hash code, so that's working for us. So in pretty much every case, I would not bother with trying to think up an algorithm for myself. Every element you've got inside your class will have its own hash code, and so we can use hashcode.combine to put them together. You'll notice actually that combine only has 8 overloads. So with that static method combine, you can only combine up to a maximum of 8 elements within your class. You could obviously use it kind of recursively, but actually the other thing we've got with this, if you've got a lot of items, you can actually create an object of this struct, and then that has a method called add. So we could add x and add y, and then just return hash dot to hashcode, and that would behave in exactly the same way. And I wouldn't use it in this particular case, but if you had more than 9, I would build it up step by step like that. Now, having seen how we can create hash codes, how do we actually use them? Well, there's lots of places they can be used, but I think the easiest example is to show how they work if you've got a dictionary. So let's put that together. So let's have a dictionary for which the key type is going to be our point C, so our class that's got the hash code. And so it's the key type for which the hash code matters. The value type, let's just have a string there, and let's just call this dict equals new, all of that. And what I'm then going to do is put into the dictionary each of those points. So I'm going to say dict dot add and then C1, and then just have a string C1 so we can see what's in there, and then same for C2, and then I'm going to look up another one. So let's do a point tester equals new point. Let's actually make these different, so we'll make that one 100, 300, and then our point, let's make the same as C1. So it's a different object, but it's got the same value as that point C1. So we should be able to find that. So what we can do is we'll say if dict dot contains key and then tester, then we will print out the value that we can look up there. So dict square brackets tester, else, and then we'll just print out not found. And so we should see that if we do that, it finds C1. If we were to change the value of the tester to 300, that would find C2. And if we were to change it to 400, it would be not found. Now that search, if you've got a large number of elements in your dictionary, needs to be very, very efficient. And what it doesn't want to be doing is, when it compares each item, to be calling equals and going through that code every time. Because even there's quite a lot going on. And if these were complex objects, then that would really slow things down. So what it actually does is it simply looks up on the basis of the hash code and uses a very efficient algorithm for searching through a collection of integers to find the right one. So what we'll see is, if we put a message in here, so let's just put a console write line and just say here, calling get hash code, then we'll see when we run that now that we've got these various call and get hash codes that are going on. What we'll also do, let's actually put another one of those in the equals. What we'll see here is it never calls the equals because it hasn't found a matching hash code. But if we were to go to our program and change it back so it does find a match, now we'll see that as well as doing the get hash code, it also does an equals. It's called it twice actually, because we've got it happening once on the contains key and another one on the lookup. So that's where we're getting it twice. So what it does is it uses the hash codes as much as possible to do its search, but once it finds two elements with the same hash code, although that's very probably a match, because it's possible to have duplicate hash codes, it then does the equals as a final check. But it's much, much more efficient because it doesn't have to do this equals lots of times. It just does it once at the end of it all. So that's why when we find something, we see that it's calling the equals, whereas when we don't find something, although it calls lots of get hash codes, it never bothers to call the equals. What that also means, though, is we've got to make sure they match up, because if the logic of your get hash code and the logic of your equals don't align, then you're going to have problems. So if we, for example, were to comment those out, and then if we run that, so you would expect to get a match because 100, 300 matches C2, but in fact we get a not found because although it'll have matched the hash code, when it then tries to do the equals, that will fail because it's got the original equals which does the reference comparison. So that's why we do these things in sync so that we get the correct behavior. And that's used in lots of situations. It's used in things like switch statements, that sort of thing, all based on the hash code. Couple of caveats there. One is that you can't guarantee that hash codes are going to be the same over multiple runs of the same program. The rules of .NET say that over a single run of a single program, the same data in objects should give you the same hash code, but if you run the program again, it's not guaranteed that you'll get the same hash codes. So if we, for example, take our record, so let's just look at R1 and write out the hash code for that, then we see at the end we're getting 205.3968.310. If we run it again, we're getting exactly the same thing. So the way that's been implemented, we're always going to get the same value. Whereas on the other hand, if I were to say create a string and print out the hash code of that, then we get 13686, 13248. So we're getting different values on each of those iterations. But what it means is you never want to do something like save a hash code into a file or a database and then expect to be able to match that in a later run of the program, because they're only guaranteed to be the same over the run of the program. The other thing we need to watch out for is that if we are doing like what we've got here, which is using hash codes on the key type for our dictionary, we should have immutable types, because there's something to notice here. If I put in just a message to show where we are in the program, and then we run that, we'll see that it calls get hash code during the add phase. It also calls it during the lookup phase, but during the add phase, when we insert our item C1, it's at that point that it calls the get hash code. So the dictionary doesn't just store the object, it actually stores the hash code for the object, which it calculates when you insert it. And that means if your keys are not immutable, so let's cheat that for now, put that as a set, we could do something like this. We could add them in there, and if I were to then change the value of C2, so let's say we're trying to look up point 100, 400. So I'm going to change C2.y to be 400. So that now you'd think would look up C2 because they match up, but when we run it, we'll see we're getting a not found. If we'd done that before we did the add, then that would be fine because it's taken the hash code after we made the change, but if we have it afterwards, it doesn't work. So got to be careful about that. So if you have got mutable objects, make sure you don't change them after you've added to the dictionary, but much, much simpler, if you just make it immutable, then you won't be allowed to do anything like that, and so you won't get into trouble. And so you can see once again why immutability is such an important concept in .NET programming and why that's the best practice, certainly when you're dealing with something like a record. So that was our look at equality. Number of things seen there. Double equals and the not equals, not too much to worry about. We've got two equals methods that we get from the object-based class and the IEquatable interface. We should make those two work in sync and basically have one calling the other. But if you implement those, then you should also put in this get hash code, and your get hash code can use that hash code struct to combine your individual elements and produce a code for your object based on its value. So, slightly obscure area of C# there, but one, if you're going to use it, you need to understand what's going on. Hope you enjoyed that. Do click the like button if you liked it, do subscribe, and I'll see you next time.